Given this array, how many continuous subarrays have a sum exactly equal to 3? Here's one and here's another. We could keep checking every possible subarray. But there's a much better way. One approach is to choose every possible starting position, then keep extending the ending position. It works, but as the array grows, the number of ranges grows quickly. For an array of size n, this takes O of n squared time. That's a lot of repeated work. So, can we reuse something we've already calculated? In the previous episode, we saw how a prefix sum keeps track of everything we've added so far. As we move through this array, our running sums become 1, 3, 4, 6, and 5. Now here's the important part. Suppose our current running sum is 6, but we want a subarray whose sum is exactly 3. Think about what that means. If the total so far is 6 and the part we want is 3, what must the sum before that part have been? 3. That's the key. Instead of searching for every possible subarray, we can ask a much simpler question. Have we seen currentSum minus K before? We know which prefix sum we need. Now we need a fast way to answer one question. Have we seen it before? That's where a HashMap helps. Instead of searching through every previous prefix sum, we can look it up directly. And on average, that lookup takes constant time. But there's one important detail. We don't just need to know whether a prefix sum exists. We need to know how many times we've seen it. Imagine the prefix sum 4 appeared at 2 different positions. Later, our current sum becomes 7. 7 minus 3 gives us 4. And because we've seen 4 twice, there are 2 possible starting positions for a valid subarray. So our HashMap stores prefix sum to frequency. There's one more detail before we run the complete algorithm. Before processing anything, our running sum is 0. Think of this as an empty prefix we've already seen once. So we start the map with 0 mapped to 1. Now if our running sum becomes 3, 3 minus 3 is 0. We find 0 in the map and correctly count the subarray that starts at the beginning of the array. Now let's put everything together. We start with a running sum of 0, a count of 0, and 0 mapped to 1. For every number, we follow the same pattern. Add, find the target, look it up, update the count if we found it, then store the current sum. First, we add 1. Our running sum becomes 1. 1 minus 3 is negative 2. We haven't seen negative 2, so the count stays 0. Now add 2. Our running sum becomes 3. 3 minus 3 is 0. 0 is in the map. Once. So we've found our first valid subarray. Count becomes 1. Then we store the current sum. Next, add 1. Our running sum becomes 4. 4 minus 3 is 1. We've seen 1 once. Another valid subarray. Count becomes 2. Store 4. Next, add 2. Our running sum becomes 6. 6 minus 3 is 3. We've seen 3 once. That's our third valid subarray. Count becomes 3. Store 6. Finally, add negative 1. Our running sum becomes 5. 5 minus 3 is 2. 2 isn't in the map, so the count stays 3. And we're done. 3 valid subarrays. Notice the pattern. Add. Look for sum minus K, count the matches, then store the current sum. And now the code is just the animation we already understand. First, create the HashMap and initialize it with 0 mapped to 1. Then keep a running sum and a count. For every number in the array, add it to the running sum. Next, look for sum minus K in the HashMap. If we've seen it before, add its frequency to the count. Then, and only then, store the current prefix sum. Finally, return the count. That's the entire algorithm. We process every element exactly once. And each HashMap lookup and update takes constant time on average. So our total time complexity is O of n. The HashMap can store up to n prefix sums. So the space complexity is also O of n. Before we finish, remember these 4 common mistakes. First, don't forget 0 mapped to 1. The empty prefix matters. Second, store frequencies, not just whether a prefix exists. Third, check the map before storing the current sum. The order matters. And finally, a standard sliding window doesn't reliably work here when negative numbers are allowed. So remember the pattern. Keep a running sum. Look for sum minus K. Count how many times you've seen it. Then store the current sum. Prefix sum plus HashMap turns the problem into an O of n solution. Next, we'll use a completely different idea to solve another classic subarray problem, finding the maximum possible sum with Kadane's algorithm.